Okay, welcome back. Last time we talked about type systems and how to derive constraints from abstract syntax trees using a type system. Next, I want to talk a little bit about unification algorithms that exist to actually then resolve the constraints that come out of these type systems. So like I already explained, there is this very basic linear time algorithm by Patterson and Wigman, but that only works for finite terms. That's good enough for the kind of mini language that are defined so far. But I also want to explain to you some algorithms that are useful for cases where you can also have recursive type definitions that are useful whenever you have recursive data structures. And for this, let us assume that we have a little program in a C-like language. Let me walk you through this because some of you may not be very well acquainted with that syntax. So here we are defining some variable p, some local variable of some type. So var is basically just saying this is having some type. We're not really specifying exactly what it is. And then here we are assigning p, basically a new memory cell. So this is allocating some new memory cell and memory, and it's just initializing it with null. So there's nothing in there, okay? And then here we are dereferencing that pointer p that we have just, that is now pointing to this memory cell. We are dereferencing this, and then we are putting something into that memory cell that is referenced by p. And what are we putting in there? We are actually putting in the reference p itself. So basically after this you will have a cyclic reference, right? So p will be pointing to a memory cell that itself holds a pointer to the same memory cell. Okay, that's why we have well, basically it's the most basic recursive data structure you can think of. But now let's see why this becomes interesting when we are generating type constraints out of this. So as I already explained, null is basically represented by a type variable, right? So it can basically be assigned to anything. And then out of this expression here, which allocates a memory cell initialized to null, well, we basically then have, so this is returning an address of something that contains null, right? And this we are denoting by this type constructor here. So we have this ampersand that is the address of operator. So we are basically defining that the type of this expression here is the address of whatever type we have for null. Okay. Then this here is being assigned to p, and then obviously the type of p has to be the same type as whatever type we have on the right hand side. So this gives us this third constraint here. But now the interesting part is here, due to this constraint, we now have the situation that the type of p is actually again also the address of whatever type p has. Okay, so here we have this recursive definition that we also get to this cyclic pointer assignment that we have here. And so for this, you will then also get a recursive solution. So it is a solution, but it's a recursive one, right? Which is saying that the type of p is actually some type alpha, where alpha again is ampersand alpha, right? So it's the address of alpha. So it's not a ground type, so to say, right? It's not concrete. It has still type variables. But you can see it as a solution, and in practice, it can actually make sense to allow such types because we want to have recursive data structures. And in some languages, they are even defined that very well. What's important to understand here is that there are different kinds of these recursive structures. Namely, you can have so-called regular terms, which are infinite, but they are also eventually repeating. So in the most simplest form, you can have something like this here, e. But you can also have such a self-repeating form like you see here, where basically the second parameter is always replaced by the structure itself, and so on. A structure or a term is called regular if it has only finitely many different subtrees. So therefore, these here would all be considered regular. But down here, you see actually a non-regular term because here you basically have different recursive structures and that don't really fit this model. If you have a type system that only generates regular terms, and that's actually a common property that you very frequently have, then you can actually also use so-called regular unification, as was defined by Hood in 76. And the unification problem for such regular terms that can be solved in that particular time constraint here, where a of n is the inverse Ackermann function. So I'm not going to go into this, but the thing is that this is actually relatively small, right? So it's relatively efficient. And the way to obtain such an efficient implementation is using the so-called union find algorithm. It's an algorithm that you may have heard of. So union find basically consists of two operations, a union operation and a find operation. And it's basically gradually comprising larger and larger unions of different elements in a partition. And then it also has a find operation that allows you to quickly find out for every individual element which class in that partitioning it currently belongs to. The point is that this union find algorithm can be implemented quite efficiently, and it can be used to represent these equality-based type systems like the ones that I showed you, because essentially whenever you have an equality constraint between two elements or two terms, it basically means that they have to become elements of the same class in your partitioning. So you are basically putting them into the same class, and you are doing that through the union operation. And therefore, union find is a very natural representation of what's going on when you are processing such a constraint system that is based on equalities only. And here's a very simplified form of this union find algorithm. So essentially, you're identifying a partition in your partitioning, or a class, you could also say, by some parent element, right? So it's a tree structure. And initially, we're just saying that the parent of some input value x is x itself, okay? Then we have a find operation that is basically traversing this tree structure to find the representative of the current class that you are looking at, right? So if you're trying to find the class that x currently belongs to, then it can be either x itself, if that is still, the initialized parent. But if that's not the case, then you just walk up the tree structure until you find something. Then if you do a union between two elements x and y, you basically find their representatives. If they are already equal, then they're already in the same class, so there's nothing to do. And otherwise, you just pick one of them. So let's say x, and you set x its parent to actually be y. So you're basically unifying these two representatives to just one. And you can implement the unify procedure just using union and find to unify these terms. Now, sometimes you will see a ranked version of this that is still extending this through some rank value that you see here, which is then incremented in such a way that basically you have the property that you get a rather balanced tree structure. So that's important if you want to get these runtime characteristics that I talked about, if you want to have an important implementation. Again, I'm not going into too much detail here. If you're interested, you can look up more on the internet. I'm also going to be posting a link to a nice video that actually explains union find in a bit more visual terms, much more better than I could do that here. So just take a look at this video yourself. If you then want to use union find in such a type system setting, you're basically representing different kinds of types through these constraints, so including type variables. So you then map from the AST nodes to different type variables. You apply the union find algorithm, and then in the end, when this has been done, you report type errors if the unification fails. And also when unifying a type variable with, let's say, a function type, it's always useful to pick the function type as representative. So I talked about these representatives that represent classes in the union find. So that's typically a good choice to make. And then for outputting solutions, it's actually sensible to assign names to type variables that are roots. But you have to be careful about type variables that are used to resolve recursive types, because obviously in the reporting you don't want to get into an infinite loop or so on when you're actually printing these types. Okay, let's take a look at some function and how this could work here. So this is again some C-like function definition that you see here. What it does exactly is maybe not so important. We only want to talk about its types. What is interesting here is that we have this second parameter x here, which down there you see it's actually being used as a function type. So here x is a function pointer, basically. We are calling the function x with q and with x itself. And this makes sense because here in the main procedure, so to say, we are actually initializing this call to foo by foo and foo itself. So by the way, this is parameterized here. This also again will be calling foo and passing foo as an argument. I hope you don't program like this, but yeah, this is just to show when such recursive types can actually be useful and when they can occur in practice. So you can try this out at home, but if you go through this program that I just showed you one line after the other, you hopefully come up with a type assignment that looks something like this. And what's important about this is that you can solve this then using a union find algorithm, and you will get the type assignment that then looks like this, and it does not actually contain any type errors. So you will, for instance, assign the address of an integer type cell to P and to Q and so on. And then we still have this placeholder here that is the type of X and foo. And that is the regular type that is the unfolding of this one. So it's basically, it has to do with this recursive call that I showed you about, right? So the first parameter was always this address of an integer variable. And the return type is always int, but the second one is again the type itself. And there's actually a way to write this in a closed form. So you can define this type to be basically lambda alpha, where then alpha is again the type variable that we are referring to. And all the other variables are actually assigned int. Sometimes you may also have infinitely many solutions. For instance, in a C-like language, you can have a function that looks like this. So here it takes something as an argument, and it's returning a pointer type or an address type, you could say, to the same thing. And so this is basically having this form, right? So you're actually giving some address as an input, and then through the dereference, you're actually getting this type as an output. And that is for any type alpha, right? So this could be of type int, could be some other pointer type. It doesn't really matter. But this is not really expressible in our current type language. So that would again need some extensions. Then I also want to briefly talk again about this slack that I mentioned earlier. So like I said, there are some cases where you would like your type system to maybe be a bit more flexible, but where it's not always easily possible. So let's take a look at this program here. So it's having some identity function defined. So that is just returning its argument of whatever type that argument X may be. And then here we are actually using this identity function in two different contexts. We are here initializing it with an object type, and here we are actually initializing it with some integer type. And now this code can run without errors, right? So because this is an object type, we can dereference f, assuming that C actually has an f field. And also here, if this then returns an integer, we can, add 42 to it. But the problem is that this is not typable, at least not in the system that we discussed, because actually we have the situation that this type here would so this type of X would at the same time have to be this class type C, but also this class type 42, right? So the type system would attempt to assign, independent of any control flow, two different types to the same variable as it is declared here. And that just doesn't compute, right? That's impossible. What you can do though, and that is then so-called let polymorphism. So that's the official term for it. You could try to analyze this definition here before you are analyzing all the different contexts in which IID is actually called. And then you could assign it such a type, right? That's basically saying I'm returning whatever was given to me, right? So whatever type. And then you could instantiate that later in both different contexts independently from one another. So that's something, if you have a type system that supports let polymorphism, then this will become typable. So that's a possibility. But there are also limitations to this. So let's take a look at this convoluted piece of code here, which I also hope you're not going to be writing actually. So here, this is a recursive procedure, right? So this is calling itself. But the point is, at the first call, this integer parameter is 1. So we are immediately going into this else branch here, right? Because x is not 0. And in this else branch, the first parameter g is ignored, right? So we're only using that in this branch here, but we're not using it in this branch. So at the first call, the g parameter is going to be ignored. In all other calls, this is also going to be an integer, right? So g is usually an integer type value, but because it's ignored in the first call, we can be evil here, and we can give it some other type value, right? So like null, for instance. And I mean, that's really evil, right? Because it's only true for the first call, really, right? So for the first call, this value will be ignored. So it's okay to give null to this. But then the challenge is now, how can you type this, right? And you cannot type this using let polymorphism because you have this recursion here, right? So we cannot assign a type by just analyzing polyrec itself that would satisfy then this constraint. That won't work. If you analyze just polyrec itself, it will assign type int to G, right? And int doesn't type with no. Then also what's important again is that all the type systems that I talked about, they're all flow insensitive, right? So that means if you have a situation such as here where you are assigning reference type to X, but then you're overriding that value later with some integer type before X is actually being used, then this code is actually from a runtime perspective, perfectly fine, right? So this will run, you will have no type errors at runtime, but the point is in none of the type systems I explained so far will this be typable code, because all of the type systems, they are seeking to assign one and a single type only to X. And this has to be a type that is valid through all of X's lifetime, right? So the same type of X has to hold here and anywhere else where X is being used. So all of these type systems are flow insensitive. They don't consider the control flow of the program. You can also have other programming errors which typically go beyond classical type errors and are typically not being detected by type systems. Like I said, there are now these blended versions, so type systems have become more expressive in recent years. And some people have developed type systems that seek to capture something like that. And you can argue about whether it's still a type system or not. But typically, if you look into compilers, how they implement type systems, these cases would often go beyond what's typically done there. Dereference of null pointers, for example, that's something that's normally not done within a type system that would rather be done through a sort of regular static analysis. Reading of uninitialized variables, yeah, normally if you see an int-type variable, that doesn't really tell you whether that variable has been initialized or not, right? So there can be type systems where you sort of augment the actual type with some other metadata, right? Signaling whether this int type variable has been assigned or not, or initialized or not. And you could still call this a type system, but you know, typically a regular type system would not take care of this. Then things like division by zero, escaping stack cells, dangling pointers, incorrect calling sequences, all of this is not what's regularly done in type systems. There are exceptions, like I said, but normally that's done rather through static data flow analysis. And so, yeah, other kinds of static analysis actually match these problems. In particular, many of these problems here, probably even all of these, they require flow sensitivity, so the statement order matters. And that's something that we are going to be talking about next week, how to cope with that, knowing what we know about type systems, how do we move to a system where we actually can consider flow sensitivity, where we do consider the order of statements, so that we can actually decide such problems here, such challenges as well. I will be talking to you then. Thank you very much for your attention.